Hi all and welcome back. In this section, section 7.4, we're going to be looking at exponential growth and decay, which gets us into a very special differential equation, which is called separable. And as you see here, a differential equation is separable if it's of the form dy dx equals f of y times g of x, which means we can separate it out and write it like this. And so we can integrate this piece, we can integrate that piece, and so we get the solution by simply integrating each side and then hopefully solving for y. So that's a special kind of differential equation, and as I said, we'll be looking at that throughout this particular lecture. Okay, so here's an example of just such a separable differential equation. And so if I separate the x's and the y's, here's what we're looking at. Okay, and then all I'm going to do is integrate both sides, and what that gives me is the ln of y is equal to 1/3 x cubed plus a constant. Now remember that when x is 0, y is 1. So I make that substitution, and I get the ln of 1 is equal to 1/3 times 0 cubed plus c, and you know that the ln of 1 is 0, so this implies that c is 0. And so therefore what we have is ln of absolute y is equal to 1/3 x cubed, and we can solve for y, and we get y is equal to e raised to the 1/3 x cubed, and that would be our final solution to this separable differential equation. So let's talk now specifically about this concept of exponential change, and that can refer either to growth or decay. And the two big examples that you are well aware of is we say something grows exponentially if the more there is, the faster it grows, and something decays exponentially if we know that as there's less and less of it, it decays slower and slower. So here's the physical aspect of what exponential change means. If we choose to let m represent the amount of stuff that's present at time t, and that stuff might be kilograms of a radioactive material, or number of people, or number of bacteria, just whatever it is that's changing, then the whole point about exponential change is that it satisfies this differential equation. And what I want you to understand here is that the rate of change of whatever it is directly proportional to how much there is. So if it's growing, the more there is, the faster it grows, and that's what we talk about exponential growth, it just gets so steep. And if it's decay, as this gets smaller and smaller, the rate of change gets less and less. So now we'll look at this with some examples. Okay, so here we are. Here is our differential equation, that the rate of change is directly proportional to how much there is. The more there is, the faster it changes. The less there is, the slower it changes. And furthermore, let's talk about the initial amount. In other words, the amount of this stuff at time 0. And we usually use m sub naught or p sub naught to represent the initial amount. Now, k is a constant, and so what we're going to do is simply separate this, and we get something that looks like this. Okay, and then we integrate, and that implies then that the ln of m is equal to kt plus a constant. Notice we don't need absolute value here because whatever we're talking about is always positive. Alright, so if we solve for m, we get m is equal to e to the kt plus KT plus a constant, which can be written like this. Now, E is a constant and C is a constant, so therefore e to the c is a constant, and we can write this as some constant a times e to the kt. Now remember our initial condition, that when t is 0, m is equal to m sub naught. So if we make that substitution, we have m sub naught is equal to a times e to the k times 0, and k times 0 is 0 and e to the 0 is 1. So this implies that a is equal to m sub naught, and so therefore we have our final equation that works for either exponential growth or exponential decay, and it will always look something like this. And what you'll learn soon enough is that when we have growth, this k will be a positive number, and when we're looking at decay, k will be a negative number. But regardless of growth or decay, as long as we satisfy this differential equation, this is the solution. Alrighty, so let's look at this example. This is an example of exponential growth. We're talking about how our population is changing, and we're told that the annual growth rate is 5%. So the more population is, the more people will be changing. And we're given some data that in 2010 the population is 1,000. We want to know how long until it gets to 2,500. So we can immediately begin by saying that dp dt is equal to 0.05 p. That's the rate of change. And if we separate, we get 1 over p. dp is equal to 0.05 dt. If we integrate and we solve that for p just as we did before, knowing that when t is 0, so we'll say t equals 0 means the year 2010, then here's what we get. We get p is equal to 1,000 times e to the 0.05 t. Okay? And so what we want to do now is solve this. And we want to know what is t if p is 2,500. So 2,500 is equal to 1,000 times e to the 0.05 t. And if we solve that on our calculator, we get t is equal to 18.33 years. And so to answer the question, it would be in year 18.33, so 2028.33. So we had 18 to 2010. And that's a solution of an exponential growth type problem. Okay, so let's talk about radioactive decay. You should remember, should have learned at some point about half-life. Half-life is simply the time it takes for a radioactive substance to lose half of its mass. So consider the little problem that we have here. If we start with 120 grams of something called tronium, and it has a half-life of 15 years, what we want to do is be able to express the mass in terms of time t. Yeah, I see it. I wrote if instead of. Well, we'll live with that. So what we know is that m is equal to m sub naught times e to the kt. That's our standard equation. And we know that in 15 years it will lose half of its mass. In other words, m of 15 is half of 120, or 60. So if we make that substitution, we have 60 is equal to m sub naught, which is 120, times e to the 15k. Alright? So what that gives us then is 1/2 is equal to e to the 15k. And if we solve that for k, we get k is equal to the ln of 1/2 over 15. So that's an important intermediate result. So what we want to do now is substitute. And so what we have is m is equal to 120 times e to the ln of 1/2 over 15 times t. And we can break this up and write it as e to the ln of 1/2 raised to the t over 15. And so you should know enough about your theory of exponents to know that this is going to be 120 times 1/2 to the t over 15. And that's our final result. And let's just take a second and think about that. So here's what we know is, if we're given the half-life and we know what the initial amount is, we can always write it in this form. There's a half, there's the half-life, there's t, and there's your initial mass. And once we have this equation, we can answer any type of question, such as, what will the mass be in 50 years? Or how many years will it take for the mass to decay to 5? So that'll conclude our work on exponential growth and decay. It's an interesting topic. It's one that you've probably seen in Algebra 2 and again in pre-calculus, but now you see how the calculus of it works. Okay, see you next time. Ciao, ciao.